Hello, algebra students, and welcome to section 4.6, where we're going to be looking at some applications of exponentials and logarithms. This is going to be discussing the exponential growth and decay. Now, you'll notice that the exponential growth or decay function is listed right here in this gray box. And what I really want to point out to you is that it looks a whole lot like our continuously compounded equation, where this original y here is going to be my future amount, my y sub naught or my y sub 0 is going to be my initial amount. I have my e, which is a number, my k is a constant, and it's going to be a rate of growth or a rate of decay. And my t is going to be my time. So it is very similar to that compounding continuously equation. Let's look at this first example that we have here. And the reason that these are numbered, interestingly, I did not start with number 1, is because they match up to the textbook examples. So anytime you want to see a similar example to something I'm doing on a video, you can go to the textbook, and in this particular case, you can go to example 2A in the textbook, and you'll see one that is similar to this one. All right, so what we're trying to do here is we want to know how long to the nearest year. So immediately I know that I'm looking for a t value. Is it going to take for money in an account that accrues interest at a rate of 2.25%, that is compounded continuously? How long is it going to take to double? So the first thing I'm going to do, compounding continuously tells me to use the equation that we're familiar with. A is equal to P times E raised to the RT power. My initial amount, I don't know. I just know that whatever it is, it's going to double. So what I'll do here is I'll just leave P as my initial amount and 2P as my future amount because it's going to double. Notice that I've written my interest rate as 0.0225, and since I don't know t, that is my unknown. I'll divide on both sides by p. When I divide on both sides by p, I'll just get 2 is equal to e raised to that power. Then I can log both sides, and I'll use my properties from previous sections, knowing that this right here, natural log of e raised to any power, is just simply going to equal my power. Again, you can look at past videos for that information for those properties. And then I'll divide on both sides by my decimal, plug that into my calculator, and let's take a look at what it says here. We're supposed to answer to the nearest year. So this is going to be then, my time is going to be approximately 31 years for my amount that I invest to double. All right, let's look at 2B, still looking at some finances here. So we have Russ, who is self-employed, wants to invest $60,000 into a pension plan. His investment offers 2.75%, again, compounded continuously. So that's going to tell me right away what equation to use. Once again, how long? I want to know how much time to the nearest hundredth of a year is it going to take for his investment to grow to $70,000. So we'll go ahead and plug in our number. 70,000 is the future amount, 60,000 the initial amount, and then my rate written as a decimal. My time is unknown. So let's divide on both sides by 60,000, and I went ahead and reduced. 70,000 divided by 60,000 is 7/6. Then I can log both sides. At that point, on the right side, I will just have my power left over, and then I can divide on both sides by my decimal, plug that into the calculator, and I will get this decimal. My directions say that I should estimate to the nearest hundredth of a year. So this is going to be approximately 5.61 years. All right, example number 3, we are using exponentials to model population growth. So let's start out by reading the question. According to the U.S. Census Bureau, the world population reached 6 billion people during 1999 and was growing exponentially. By the middle of 2018, the population had grown to 7.504 billion people. The projected world population, T years after 2018, is given by the following function. So we were handed an equation, and you'll notice it looks a whole lot like our equation that we use for finances, but we also go all the way back. It's this equation right up here, where y sub 0 is going to be my initial amount, y is my future amount, etc. All right, one thing to notice that it says that the projected world population T years after 2018. So we're going to consider then T equal to 0 at 2018. 1 year after 2018 is going to be 2019, so my T will equal 1. 2 years after 2018 is going to be 2020, so that's going to be my T value of 2. And so part A says, based on this model, what would be the world population in 2020? So in this case, my T value is equal to 2. So all I need to do then is I just simply need to find f of 2. So we'll plug in 2 for all of my t's. I'll throw that into the calculator and get this decimal. And essentially what we're going to do is we'll round according to what was already used, the same type of rounding, since it doesn't really say how to round. We'll round the same way that they rounded in the original question. So 7.646 billion people. Continuing on, if this trend continues, approximately when, so I want to know what my T value is, approximately when will the world population reach 8 billion people? All right, so 8 billion then is going to be my future amount. So you'll notice that I kept the right side of my equation identical. I didn't change anything. But for my future amount, I put in 8 for 8 billion people. All right, so then we will go ahead and divide on both sides by that 7.504 number. And then I can log both sides, use my properties of logs to get my power alone, and divide both sides by my decimal, throw that into the calculator, and I'll get this 6.838176. So once again, this is a time. All right, so what we can say then is approximately 6.8 years after 2018, my population will reach 8 billion people. So this would occur in sometime in the year of 2024. All right, let's look at some decay models. Half-life is the amount of time it takes for a quantity that is decaying to become half of its initial amount. So looking at example number 4 then, suppose you have 800 grams of a radioactive substance, and 800 grams are present initially. 2.5 years later, only 400 grams are remaining. So the first part of the question says that we should determine a function that models this. And this is going to be done in 2 parts. First thing we want to do is we want to find our k first. Now, where do you say, are we getting this k? Go all the way back to the beginning of the notes. And once again, I'm using this particular equation because it is a decay function as well as a growth function. So this is the k that we're talking about here, essentially my rate of decay. All right, so we want to find our k first. So the first thing that we're going to do then is we'll set up our formula, our equation. So 800 is how much I started with. 400 is what I ended up with. Times e raised to the r, or you could use k, times 2.5 years. All right, so we'll divide on both sides then by my 800. 400 divided by 800 is a half. And then we'll log both sides, use my power property to get my power alone. Notice one thing that I did do here is that I used the quotient. Sorry about that. I used the quotient rule to take. Okay, let me get that back there. To separate my single log into 2 logs. where I have the log of the top minus the log of the bottom. Remember that any log of 1 is 0. So this is just going to be a negative natural log of 2. And then I'll divide on both sides by my decimal, throw that into my calculator, and I'll get my rate value or my K value. So then what I can do is I can plug this into my function. And so I'll have y is equal to my starting amount of 800 times e raised to my rate times t power. All right, so then I can use this equation for part B. How much of the substance is going to be present after 4 years? So let's go in and we'll, for our time, we'll plug in the 4. So using this equation, plug 4 in for t. Throw that into your calculator, and that's going to be 263, or rounding here, 264 grams. And again, remember that the original was using 800 grams, so we'll round in the same way that the original was rounding. So that's why we chose to round to the nearest whole number of grams. All right, example 5, we have a carbon dating question. So carbon-14, also known as radiocarbon, is a radioactive form of carbon that's found in all living plants and animals. After a plant or an animal dies, the radiocarbon disintegrates, and scientists can estimate the age of the remains by comparing the amount of radiocarbon with the amount present in current living plants or animals. This technique is called carbon dating. The amount of radiocarbon present after T years is given by, and we've given you here an equation. Once again, this is my future amount, y sub 0 is my initial amount, t is my time. So let's take a look here, find the half-life of carbon-14. And so the first thing I'm going to do is I skipped a step here. But basically, if you can think of y sub 0 being replaced with a present value, and then y being replaced with half of that present value, if you divide on both sides by p, you're just going to be left with a half. So that's how I magically came up with that half. And then the other side I just simply copied. So finding the half-life, then we'll log both sides, use our power rule, divide by the decimal, plug it into the calculator, and the half-life of carbon-14 here is going to be approximately 5,700 years. All right. Part B, suppose that the skeleton of a woman who lived in the classical Greek period was discovered in 2005. Carbon-14 testing at that time determined that the skeleton contained 3/4 of the amount of carbon of a living woman of the same size. How long ago, to the nearest year, did the Greek woman die? So the first thing that we'll do is we'll write our formula. And once again, since I have 3/4 left over, you could think of this as my original amount was P. I have 3/4 of P left over. Divide on both sides by P, and I'll just have that 3/4. So that's where that came from. We'll log both sides, use my power rule, divide by the decimal, plug it into the calculator. This says to the nearest year, so approximately 2,366 years ago is when this particular woman died.